ceremonial pole. You know, they have races around here. They put big races around here, and of course, it's the race around the world. And you know, anyway. So here we were. It looks like we're ice fishing, but in fact, what we're doing is getting the foundation ready. We're going to put this enormous telescope down there, and it's going to be on snow. You can't dig down. It's 2 miles thick of snow and ice, so you have to float it. And that's getting it ready. Here we are building the float. We've learned that everything you build down there that's exposed to the cold will fail. And every time you try it, you learn another way something can fail. So what we do is we don't try anymore. We put all the moving parts inside, all that we can, and build the telescope in buildings and stuff. This is this backup structure that's going to hold the mirror. Very high tech, actually. The mirror is going to be 10 meters in diameter, and it holds at all angles and at all the temperatures that surface to a precision of the width of a human hair, over 10 meters. So it's a very precise telescope. So this is what it looks like in the summer. You know, it looks warm, not too bad. That's what it is. It's sunny, but it's cold. And in the winter, of course, this thing's pegged. The average temperature in the winter is about -80. Fahrenheit, and I think the record is -118 Fahrenheit, without wind chill. So that's what it feels like. Here is setting the surface for this telescope to get that precision. There's I think 750 adjusters, all adjusted to a micron and readjusted and measured out in the cold. That's Jeff McMahon. And this is putting this kind of all together. You can see the telescope emerging through the building here. A 2-crane lift of this very high-tech carbon fiber and very precise surface on top. And the whole station comes out. In the summer, there's about 200 people on station. They all come out for this. And you think they're, you know, they're real supportive. And what it is they figure, you know, if you're going to drop this, they don't want to miss that. So just in case, they all you know, weather the cold and come out. But we didn't drop it. We got the telescope working. And here's a more recent picture of it. It's huge. It stands about 6 stories tall. It's the largest telescope ever deployed on the continent. And you can kind of see what it's like. Here's the crew up there in front of the mirror, the students. And this is the group of people that I'd always like to point out. So the South Pole there's a station there. It's operated year-round, but you can only get in and out between early November, maybe the last week in October, to about the 10th of February, 12th of February. That's it, about 3 months. But all the best conditions, especially for the work we do, is in the winter, their winter, our summer. So we have to hire people that are going to be our eyes and ears and hands and be there just overnight. So we're always looking for these people, and these are really our true heroes. They're fantastic. We had Steve Payton, who was actually the main project manager, did it the first year with the graduate student, Zach. You can see some of these people. Dana Hrubes, what a hero, 2008, 2010, and 2011, 2 years in a row. And 2013. So these people are great. And of course, they like to, you know, it's -40 or 50, and they're just posing there. Anyway, we get it all together. We have this camera, millimeter camera, which we have to make by hand. We have our detectors. You know, we're on a cold site, but our detectors are really cold. They're at about 500 milligrams, 1/2 of the degree above absolute zero. So we can make these measurements. And here's then the map, the first map we've made of a large part of the sky. It's about 1/16 of the sky. And, you know, this is what WMAP had done. This is much, much higher resolution, but you can't tell. There's arc-minute resolution. So let me blow it up and show you what this all looks like. So here's that WMAP, that picture of the sky done by the satellite, but blowing up so you can see some of the detail. And this is that structure. This is the baby picture of the universe. A new satellite recently reported results, very successful ESA satellite called Planck. And there it is. It's more sensitive. has about a factor of 2 higher resolution. And you can see, the structures are there, a little more well-defined. And then here is for that same region from our telescope. Now, not a satellite, but a big 10-meter telescope, and much more sensitive for this part of the sky, but we didn't do the whole sky, right? And you could see a number of things. One is this cloud-like stuff. I don't know why we're getting shadows in here, but that's real. That's the cosmic microwave background. That's what it really looks like. Our resolution is 50 times better than that. In fact, you can see what our resolution is because you see all these bright spots. Those are galaxies that are emitting at these wavelengths. You couldn't see those at the sensitivity and resolution of the other experiments. So we can take a spectrum now of that, do the same thing, what is the bass and the treble, put that together, and that's what it looks like. So here's the first peak we saw 10 years ago. Then we see another harmonic, and another, and another, and another, and another, and another, and another, and another. It's just spectacular. And remember, this is of the universe. This is sound waves in the early universe. That's the spectrum. And I don't have it here, but if you take a theory, inflationary theory, it goes through every one of these points. It does exactly that, right? And this data is now so precise that we can actually measure by analyzing this data, not just that there's 4% of the universe is ordinary matter and 20% is dark matter, but we can also tell you that there's 0.4% of the universe in energy density is neutrinos, right? And we can tell you there's 3 neutrinos, right? So we're really getting enormous precision. So let's take that filter thing map, and we're going to filter out. So what was this goal for years, was to measure those first peaks. Let's turn the base way down and show you what's left, right? So we do that. This is what it looks like. It's a slightly different part of the sky. And you see there's these bright spots. Well, those are galaxies. We now have high enough resolution where we can see individual galaxies. And we expected to see some of these galaxies, radio galaxies. They're very cool. They're black holes and stuff at the center of galaxies. But we actually found some that had the wrong spectrum. Instead, they looked like they weren't these black holes and these radio galaxies we knew about, but instead that they were galaxies forming stars at an enormous rate. And yet we couldn't find anything in any other catalog, in infrared catalogs of these galaxies. And the reason why is it turns out they're very, very far away and very rare. So this is what's going on. We see these looking very far in the past. We could see these galaxies. Normally we wouldn't be able to see them, but they happen to be located behind a very massive foreground galaxy, which we don't see. It doesn't emit much at our wavelengths. Instead, we see these then being very, very bright. And when we look at the Hubble Space Telescope, we can then see this optical galaxy. So this is research which is opening up the ability to look at very young galaxies and also learn about what causes this lensing. But that was a discovery that was totally unanticipated. But it came from making new measurements at a high resolution and doing a big survey. What about these things we're looking for? What about this? You remember ages ago I was talking about dark energy? What about that? So this is the phenomenon we're looking for. That's these things. There they are. There's shadows. We're looking at the cosmic microwave background, and we're seeing shadows. So have you ever wondered, is the cosmic microwave background really coming from the cosmic microwave background? Yes, it's behind these things. And there we see these. So it worked. In fact, this experiment was the first to ever discover galaxy clusters by this, right? So there's these enormous objects. We are now looking at these because we can find them, and because, as I said, we're looking for a shadow. No matter where they are, we'll see the shadow. We actually don't know where they are. We say it's there, but we don't know how far away it is. We have to go now and use other telescopes, knowing exactly where to look, and try to find the light in the spectrum and find out their redshift, so we can figure out where they are. So we do that using these telescopes. In this process, we find out some of them are just absolutely amazing objects, a whole other discovery of astrophysical objects. But let's go back to what we're trying to do. So here's a plot. We can figure out how massive they are, right? And these are big numbers, and how far away they are. Look back time, so how far back in the universe we are seeing. So this plot, the black points are all of our new points. So this is just showing kind of our sensitivity. And you could say, well, you know, what happened out here? And what happened out there is they don't exist. They hadn't formed yet, right? How many more are there here than there? Well, we can tell you, you can count them up. We could put together now that tug of war. We can figure out how many galaxy clusters, these enormous objects. In fact, almost all of these, especially at about this far, are new discoveries, right? So this is all kind of a new part of looking back in the universe for these objects. So we can put together this history and see, is it consistent? Was Einstein right, or is he wrong? Are we going to have to revise gravity, or does it all hold together? This is what we find. This is what we find, that in fact, that theory, it holds up. It holds up remarkably well, right? So we did this whole test. We're going to get more precision, but now at the kind of 10%, almost every other theory that would explain this is ruled out. This is what it looks like. Einstein's cosmology, was it his biggest blunder, his most prescient prediction? That is what's with us today, right? We're also finding interesting things I mentioned by getting this high precision. In the background, we're learning about the neutrinos and other things. So let me go one more thing before I end. I know it's getting a little late. Inflation. Is there a way, here we are today, we look back, as I said, we see this, develop this baby pictures, we see the early universe. How do we go back further? All right, can we look at this first tiny fraction of a second? And Andrew Lang used to love to show this engraving of, how do we get behind and look? And I don't have time to explain in detail, but there is a test we want to do. There's groups here at Stanford working on it, and we're working on it. And the idea is that if inflation is right, there should be other distortions, not just these fluctuations that we see and these early seeds, but there should be gravitational waves, space-time distortions that we might be able to see. And they would lead to not just seeing the CMB and perturbations, but this funny polarization patterns, the way the light is polarized. You wear polarized sunglasses to cut out reflected light and change things. Well, this would cause a pattern in how the light was polarized, right? Inflation could do that. And if we could see that, we would learn and test a great deal about inflation. It'd be a wonderful thing. But it's really hard. It's really a weak signal, right? I mean, the signals we're seeing now, we're getting down to about a part. We're seeing contrast of a part in 1 millionth of the CMB. We're going to have to do better than that, right? And many people have called this the holy grail of cosmology, right? If we could do that, that would just be fantastic. So we're trying this. Other teams are trying it. And what we're looking for is this polarization. The jargon is B mode. Don't worry about that. But it's polarization patterns, huge, like patterns on the sky and swirl-like patterns in the polarization on size scales bigger than the full moon, right? And so when you think about that, a picture comes to mind. Swirls on the sky bigger than the full moon, right? So I think they were trying to tell us, what to do or what they saw, and they just didn't know how to describe it. But I think that's kind of what we're looking at. It's not in the intensity, though. It's in the polarization. It's a subtle effect. So we built this camera to put on our telescope. This thing is cooled down, and these now, all these little detectors, little feed horns feeding detectors, are polarization sensitive. They can tell us about how that light is polarized. We got it on the telescope in 2012. This is Abby. She's thrilled because it's her thesis. Everyone is thrilled because we finally got this thing working. And we took data in 2012 and measured the polarization. Regular polarization been measured, but we actually found these swirl-like patterns. Now, you haven't heard about this probably, which means I'm not telling you everything. We didn't find it from inflation. It turns out there's another way you can get the swirl-like patterns, and it's from this gravitational lensing and stuff that I told you from later times. There's some polarization swirls. That's a very weak signal. In fact, we have to be able to measure and characterize that signal before we get to the other. So we have our first milestone on the way to measuring that polarization. And in fact, In fact, it was awarded this year, that measurement, one of the top 10 breakthroughs of the year from Physics World. I don't know if this, I was looking at other things they said were top 10, and I'm not so sure this is, how important it is, but it's kind of fun to show. But we're on our way. That's the message. We have this way. We're going to be able to measure that, and you may be hearing sometime soon, that, or not, about dark matter. That they've discovered the dark matter particle. That'd be great. It could happen right here. This group at Stanford doing this work. It could happen right here. That say the headlines will be discovered, inflation or B-mode patterns. It's going to happen. We're going to hit our ultimate limits, or we're going to discover it soon. So I'm going to wrap up there. But there's a cool thing going on here. You can read the writing. I mean, the main thing is this has been a great field for 50 years. I've been doing it for about 15, and it's just so exciting. We're learning about dark energy. We're now making these measurements to probe the origin of our universe at the first instance. What's next? And you can ask that question. We have an expert here who can tell you an answer. But if this theory is right, inflation, it says there was some pre-existing piece of space-time inflated, our whole universe came from it. What's next? You think about that. But the other thing is, there's a movie going on here. That's the, when you send these winter overs there, give them very good equipment, and they'll take these beautiful pictures. That's the aurora over from the southern lights, about a speed up of about 100 times going on. Anyway, thank you very much.
About the universe. There should have been another question. Are there any questions? We can take several questions if you time.
Is your group doing any of the work to look at the sort of donut-shaped pattern where another universe may have touched ours at one point in time?
So you're answering the next question, I see. The question is our group working on the donut patterns where another universe may have touched ours? So let me, the answer is we're measuring the polarization, we're experimentalists, and if patterns are there to be seen, we would be sensitive to it. Is that our main purpose, thinking that's it? No, we're doing what I said. But the idea is that, if in fact this theory is correct, there should be other universes. In fact, there should be an infinite number of universes. It's often referred to as the multiverse. And your question really is, is there a way to detect other universes in that? It's I'll leave that as an open question. Let's figure out what we can do here first. Yeah.
You mentioned these 9 harmonics you see in this microwave background. That looks to me a little bit like nuclear seismology. Sharon can explain it much better. There we have these global oscillations and the harmonics, and we see up to 500 kilometers by now.
Yeah. The analogy is not that far off. So you can look at the surface of the sun, measure Doppler shifts essentially is how they do it, and measure the oscillating modes of the sun, right? And they learn a lot about the sun, and that's one way you can learn about the interior of the sun. That analogy is not that far off. We're essentially doing that type of thing. But it's not quite that we have a surface and ricocheting. It's a plasma, and we're capturing it at a given time. It definitely is sound waves. Very low frequency sound waves. The lowest one is got a period of about 800,000 years. So low frequency. Yes?
There's a telescope coming after the Hubble. I'm wondering, is that going to be of any help to you?
There's the James Webb Space Telescope. It's a terrific telescope. It's going to be revolutionizing a lot of things. It won't help us with look at the cosmic microwave background. We're looking farther back. It's observing in the infrared, but not far from the optical, so not doing that. Where it's going to be just tremendous is looking at those early galaxies that I showed. It's going to be able to see those and pick them apart and stuff. And then for looking at the galaxy clusters that we see and trying to understand them, it'll be terrific. Yeah, it's an amazing facility. Yeah?
You have a very naive question. When approximately was the balance point then between the expansion forces of dark energy and the collapse of dark matter?
Let's see, the redshift would be about 0.6 or 7, and then so, what is that in giga years? It's about a, 6 or 7 billion years, about halfway. So, people have said this is strange. Why is it right now, while we are here, that it's very close to that balance point? When actually it should only be that for a fleeting amount of time. And so there are other models that say, that coincidence is too uncanny. It must be that they track, that there's some mechanism, some physical mechanism that tracks them. These data show that's not the case.